Okay, we are live on YouTube. And 22 participants so far. Okay. I think we should start.
Whenever you want, you're the boss.
Welcome everybody to the Monsoon Geo Seminar, wherever you are on what meridian you are now. It is my great pleasure to welcome today my colleague from Woods Oceanographic, Valier Galy. Valier is an associate scientist in marine chemistry and geochemistry department. He's done his doctorate in France, and his research, long-time research, has focused on various aspects of biogeochemistry, including carbon cycling in different environments, either terrestrial or oceanic, on the long-term paleoclimate and Earth surface processes. And he's been working on the Indian monsoon for a long time, since he did his master. And now he's going to talk about different time period, Neogene. He has sailed as an organic geochemist in the expedition drilling the Bengal Fan, expedition 354. Welcome, Vali, and thank you for joining us. And you can take over and start your magic.
Thanks. Thanks so much, Liviu, for the kind presentation, introduction. Thanks to the organizers for the invitation. I think this is definitely one of the benefits of COVID. You know, there's online seminar series that bring together various communities in a way that would be actually quite challenging if we were to try and really get together in the same place. So this has been really nice. Yeah, so I want to start with mentioning a few of the key players that have been an integral part of this work. Sarah Fickins, my colleague at USC, who's been in charge of doing much of the measurements, common-specific measurements I'm going to show today, but also Christian Franz-Lanor from CRPG in France, who was co-chief on Expedition 354 and has been doing a lot of work on the inorganic chemistry of these sediments I'm going to talk about. And then my brother Valier Galy, also from CRPG, who's been doing a lot of the radiogenic isotope work. So what I want to do today is to bring you through a tour of our work looking at those records from the Bengal Fan and try and tell you what we have learned about the long-term evolution of the monsoon, and I'm gonna try to resist the temptation to go too much into the implications in terms of carbon cycling and surface processes, because that's not really the meat of the subject for this crowd. So I'm going to try to stick with monsoon, but bear with me if I do go on two tangents talking about carbon cycling. So with that said, I just want to start with a very basic introduction on the general context for variations of the monsoon or apparition of the monsoon, I should say. So here on the left, you can see a classic stack of delta 18 benthic forams from Jim Zakos over the last 70 million years that shows the gradual cooling of the Earth from somewhere in the beginning of the Eocene all the way through the modern period and the apparition of permanent ice sheets at both the South Pole and the North Pole over time. And this, of course, is mirrored by long-term decline in CO2, atmospheric CO2 levels. It's a bit of an outdated compilation of data here, but it gets the point across, which is that, of course, as you go from these really warm times in the Eocene towards cooler and much more climatically variable times, here in the Pliocene, you have a corresponding big drop in PCO2, and the timing of which is a bit unclear, but that is the basic observation. And of course, for what interests us, there is the tectonic context of the India-Asia convergence shown here on the right-hand side, where you can see the rate of convergence between Asia and Asia that drops dramatically starting somewhere around 54 million years ago when the collision started. And so that slowdown in the convergence is actually matched by an increase in surrection and relief that actually created the Himalayas. And so, as you will see, and as I'm sure many of you know, the formation of this very high relief that is the result of the collision between India and Asia is playing a very important role in controlling the monsoon. And so the big question becomes, what is the interplay between all of these different things here? You know, the tectonic context of the surrection of the Himalayas that creates relief, and on one hand, and then on the other hand, the global cooling and the big drop in atmospheric CO2 that goes with it. And so in that context, there's been a lot of work to try and understand when the monsoon started and how the monsoon has evolved in response to some of these big, global variations, but also whether or not the variation in the monsoon may have played a modulating role in some of those phenomena through its large impact on surface processes and carbon cycling. Okay, so we're talking about the monsoon, and I just want to start with something very basic, but something that you will see is quite important. The monsoon, we like to, or the climate dynamicists like to talk about as a reversal of the wind patterns. And those winds that you can see here in the June to August time period, this is modern conditions. The winds reverse and flow from the equator north towards the tropic and subtropic, and that's really characteristic of the monsoon. However, there's another feature of the monsoon that's very prominent, and that actually perhaps is more important from the standpoint of either living in those areas or understanding the surface processes that are associated with the monsoon, and that is a very intense precipitation associated with the wind reversal. So you can see here over much of India, Bangladesh, and the Himalayas, very, very intense precipitations throughout the entire time period that is associated with the monsoon. So the monsoon is in that regard complex, because there is the wind reversal, but there is also the very intense precipitation. So you will see that when we talk about the monsoon, we talk about the monsoon through proxies. We have to be clear about which of these two pictures we are actually recording. So a little bit of a background on the global long-term basic fundamental controls, I should say, not basic, of the monsoon. And what really became obvious in the last 10 or 15 years is that by and large, the Asian monsoon, summer monsoon, is related to, as I said already, the relief that's being created by the surrection of the Himalayas. So here on the left-hand side, you can see a plot of July temperature at 250 hectopascals. And on the right-hand side, you can see the subcloud entropy for the same time period. And you can see there's a big mismatch between the two. So historically, up until maybe 10 or 15 years ago, there was this idea that it's the heating, the differential heating of the landmass and the ocean that creates the reversal of the wind pattern, and that that initiates and fuels the monsoon. But in fact, what climate dynamicists are telling us is that it really is the subcloud entropy that is ruling the convection. It's really the engine, the energetic engine of the monsoon. And what you can see is that its distribution is very different from temperature. And it's actually much more related with the orographic barrier of the Himalayas than anything else. And then, what people could have imagined was the control way back in the days was, the heating of the landmass. So clearly the orographic barrier that the Himalayas create is very, very important in controlling the evolution of the monsoon, at least in the present times. That's very, very clear. So this is a now pretty well-known and famous modeling work by Booth and Kwan 10 years ago, 11 years ago. And what they did is that they basically tried to see what happens if you try and generate climate conditions by removing either all of the topography here in the center or just the Tibetan plateau, but keep the orographic barrier of the high Himalayas. And what you see is in here on the left, that's the control with normal topography. What you see is that when you remove all of the topography, you completely lose the characteristic features of the monsoon, either the wind or the precipitation. While when you do keep the orographic barrier but remove the Tibetan plateau, you can actually generate something that really start to resemble the actual monsoon in terms of wind distributions and also precipitation distributions. So that gets to further demonstrate the importance of having a very high topographic barrier here that is oriented east-west and sort of like blocks the injection of cold, low entropy air from the north. So just to recap and drive that point further, this is the distribution of rain and wind in June to August in the modern times. So the wind reversal, very high intense precipitations, and here this is just a sketch that shows these like very prominent control of the operation of the monsoon, initiation of the monsoon by the very high barrier that creates the high Himalayas and stops those cold, dry air with low or moderate entropies to penetrate southward and meets and dilute this very high subcloud most entropy air that you have in front of the Himalayan range. So that's the what we understand about how the monsoon, the summer Asian monsoon works in the modern times. And so the question becomes how it's evolved over time in the context of the surrection of the Himalayas, and also, as I said, in the context of the long-term global cooling of the Cenozoic. And some of the early work about this stems from looking at records from the Arabian Sea. This is a paper by Wang in 2015. There is older records that basically show the same thing. And these records, they show very prominently an increase in proxies for upwelling or dust in the Arabian Sea somewhere in the Miocene, so tentatively around 8 million years. So these are very famous and popular records, and those records were kind of taken for face value in suggesting that the monsoon has increased, or even that perhaps the monsoon has started around 8 million years ago, because these proxies are telling us that dustiness and upwelling, which is driven by the reversal of the wind, increased at that time. So this is a very still quite popular belief in the community, in parts of the community, that the monsoon has really strengthened somewhere in the Miocene based on these records here. And I'll try to show you why this might be somewhat misleading in the context of what we've learned since then. Yeah, so if this was true, it would be entirely true. It would be in part problematic, because as I've shown you, the orographic barrier of the Himalayas, this is the relief of the Himalayas here and the Tibetan Plateau, is really essential in generating the monsoon, the summer monsoon. And what we know about when that topography has been uplifted and how long it's existed for is basically telling us that it's been there for a long time. This is just it's pretty old now compilation of studies of paleo-elevation, and you can see that across the southern edge of the Tibetan Plateau, there is very high elevations, 15 million years ago. Here in the central of the plateau, it dates even far back to 30, 35, maybe 40 million years ago. So we have good evidence that there has been high relief in the area, at least since the Oligocene. And so with that in mind, there is absolutely no reason that the monsoon would have magically started to appear or strengthen 8 million years ago, when basically we already had an orographic barrier very well established. So that puts those Arabian Sea upwelling and dustiness records into let's say that makes them slightly puzzling. To just drive this point further, we can turn to some of the work that's been done looking at fossils in the Indian Indo-Burmese range. This is a work by Alexis Licht. I think he actually gave a talk early on in the seminar series. And basically this work looking at these fossils is suggesting, based on delta O18 values and based on reconstructed seasonality, this is suggesting that there was some climate system that resembled the modern monsoon in terms of very depleted delta O18 compositions and very high seasonality as far back as in the late Eocene. So here we are now with two indirect evidence, topography and these fossil records that suggest that probably some monsoon system has been in place for a very long time. Okay, one thing that just a point that I want to make before I dive into the actual work we've been doing is talk a little bit about climate models, dynamic climate models, and how they can or cannot solve our problem. So here, this is a plot on the left of train precipitation data at a 1/4 degree resolution that shows, the prominent features of the distribution of rainfall during the monsoon here along the western coast of India, and then here in Burma and along the Himalayas. And what you can see when you look at model outputs, this is a really nice paper by Acosta and Huber in 2017, is that when you change the resolution of the models, you have a huge impact on the distribution of precipitation, but also, and more importantly, on the wind patterns. So here in this example, when you compare 2 degrees and a 1/4 degree resolution, what you can see is that at 2 degrees, you completely lose the characteristic distribution of the wind patterns here over the Indo-Gangetic floodplain, and you also lose much of the prominent features of rainfall distributions, and more importantly, of the moisture distribution vectors are here on the right-hand side. So basically what this paper concludes, and these are very prominent climate dynamicists right there telling us that, is that if you want to model the monsoon well, you have to have models that work at very fine resolution. And so this becomes really problematic if you want to set up these models for, say, the Eocene, or even for much of the Miocene, because we don't have the context in terms of paleotopography and paleogeography that is established well enough at those type of resolutions to do that. Not to mention that this is becoming a problem of computational time if you run these models for very long. So I would argue that at this point in time, we can't really turn to climate model to tell us when the monsoon has started and how it has really evolved over the Neogene because of those limitations. So with all that said, we turn to what we do, which is go on a big ship that joins resolution in the middle of the ocean and retrieve sediment core so we can apply our favorite proxies for whatever we try to reconstruct in these terms, rainfall, in this case rainfall, and try to see what we can do about reconstructing the monsoon. So we sailed in 2015, that's already a long time ago, to the middle of the Bengal Fan to drill a transect at about 8 degrees north and retrieve sedimentary records of the erosion products from the Himalayas. So this is here on the left cross-section, north-south, from about here all the way to the distal edge of the Bengal Fan. That shows sediment thickness, estimations of sediment thickness all the way from Bangladesh down to south of the equator or above the equator. And what you can see is that the sediment thickness is just astronomical. If you go here, just south of Bangladesh, you've got thicknesses in excess of 20 kilometers. So clearly, no one can drill and core this dip. And so to have something you can manage in terms of sediment thickness, you have to go in more distal locations, which is exactly what we did with this transect around 8 degrees north. Still, you have sediment thicknesses in excess of multiple kilometers at that position. And so as I said, we've drilled the transect east-west from the position of these points is weird, from the flank of the 90th ridge all the way to the modern active, most recently active channel, I should say. So about 2/3 of the width of the Bengal Fan. So I just need to talk a little bit about how sediments get there, and what these sedimentary records actually mean. This is very unlike most of the records that I'm assuming many of you are interested in and used to look at in terms of paleoceanographic reconstructions. These are detrital sediments that are brought from the continent via turbiditic flows and very rapidly deposited thousands of kilometers south of the river mouth. So this is a map of the Ganges-Brahmaputra delta here that shows the very shallow shelf here that is cut by a very deep canyon that funnels the sediments via these gravity currents, generating turbiditic currents all the way down to south of the equator. And there's very clear, very well-developed channels that run the entire length of the Bengal Fan that deliver these turbiditic currents all the way to the drill sites. So if we look at a few cross sections through the Bengal Fan, what we can see is these very typical successions of channel levee systems that get buried on top of each other. And so really we are here looking mostly at those deposits that relate to these turbidity currents that get buried on top of each other. So the one thing that is important to understand is that those channel level systems are usually not very wide, and the depot center is shifting laterally as the channel reverses and moves laterally throughout the fan, spanning the fan. As you can see here, many of the channels that are visible at the surface here are depicted on this picture. And so to capture the turbidity sedimentation at any given point in time, you really have to have this transect approach whereby you sort of ensure that you're drilling wherever the turbidity depot center is at the time you're interested in. Okay, so with that in mind, back to the central question of the talk, which is about the erosion of the monsoon over the Neogene. So of the 7 sites that we drilled at, 3 of them are long and go into the Miocene. And here you can see the depth H plot for these 3 sites, 1450, 51, and 55. 451 is on the flank of the 90 East Ridge. This is a grossly vertically exaggerated section here. And because of that, the sedimentary sequence is condensed. So we could actually reach pre-fan sediments there. But what you can see is that with these 3 sites, we have a record of turbiditic sedimentation throughout the last 20 million years or so. And obviously, during these turbiditic phases, the accumulation rates are astronomical, in excess of hundreds of meters per million years. The other thing that I need to mention very briefly is that you can see here is these logs. All of these yellow colors here are representing sand. And so you can see that here we are 2,000 kilometers south of the mouth of these rivers, and we have gigantic packets of sand are being delivered by this turbidity current. So very, very energetic system that we are dealing with. And this is just a quick illustration of this with the various classic sedimentary facies that we recovered from the classic turbidite Buma sequence, typical for the levees here on the left, to these very massive sand units that are more typical of overspill. Here in the Miocene, we see the exact same features, but they get a little more compressed and compacted, but the compaction is not actually that impressive for being a kilometer down below the seafloor. And then interspersed between all of these turbiditic sediments, there is some hemipelagic sedimentation with higher carbonate content and some bioturbiditation features and the likes. And so for the purpose of this talk, I'm really going to focus on the turbidites. I'm not going to talk about the hemipelagic sedimentation that is in between at all, because we are mostly interested in what directly comes from erosion of the Himalayas. Okay, so very quickly, I don't want to spend too much time on this, but when we looked at the composition of these sediments, this here, a plot at the top of D84, so grain size, and at the bottom, iron over silicon as a function of aluminum over silicon ratios. If we're comparing, so the grain size, the mineralogy or bulk geochemistry, inorganic geochemistry of the Bengal Fan sediments in blue, and the modern river sediments, the Ganges here on the top, and the mixing of Ganges and Brahmaputra here in yellow for the bottom plot, you can see that those turbidites, they really resemble in terms of their mineralogical assemblages and grain size characteristics. They really, really resemble what we see in the modern rivers draining the Himalayas and delivering sediments to the Bengal Fan. In terms of tracing the sediment source, this is a used and abused plot of neodymium and strontium isotopes. that shows the main lithological units that contribute to the modern sediments, the Trans-Himalaya, Tethys, the high Himalaya crystalline, and the lesser Himalaya, and all of the sediments, the turbidite sediments from the transect at 8° north. They plot like in the mixing domain between all of these Himalayan rock units, and they really, really resemble the composition of the modern sediments that fall somewhere around here. So there is some second order variability that I'm not going to go into. That is actually interesting, but I'm guessing maybe Christian is going to go into it in a couple of weeks when he gives his talk. So really, we're dealing with sediments that are derived from erosion of the Himalayas. And I'm going to skip this in the interest of time. So, as I've said in the introduction, the monsoon has these two prominent features, one being the reversal of the wind patterns, the other one being the distribution of very, very intense precipitation in the summer. And the problem in terms of understanding the evolution of the monsoon is that we have very few, if any, good records of precipitation over time. So the good news is that the monsoon rainfall comes with a pretty unique characteristic, and that is a very intense depletion in deuterium. So if we look at here a plot of rainfall throughout one entire year in blue, and the corresponding hydrogen isotope composition expressed as delta D of these rainfall events, and you can see that during the, this is a record from this place here, Galigaon, a small village at around 2,000 meters elevation in the Himalayas. You can see the high peaks, 7,500 or 8,000 meter peaks in the background here. So really the typical southern Himalayan flank location. And so you can see these very, very intense precipitation events during the monsoon period, with days when you have more than 200 millimeter in a day, and that actually happens multiple times during the monsoon. And the hydrogen isotope composition of those precipitation is really very depleted in deuterium. Compositions between -50 and south of -100 per mil during the monsoon. So this gives us a really unique opportunity to trace the monsoon through hydrogen isotopes. And the way that we do that is by studying the composition of plants that grow using rainwater, environmental water, surface water, you name it the way you want, and actually record the hydrogen composition of those surface waters. So just to tell you a little bit more about this, in the modern systems where studying these processes is quite easy. This is a recent study of looking at soils over 4 different transects, elevation transects through the Himalayas, and looking at the composition, the hydrogen isotope composition of these leaf wax compounds that are produced by vascular plants compared to the hydrogen composition of the environmental waters, like xylem waters, or surface waters, or even rainfall. And you can see in these 4 examples here is that those biomarkers, those lipids that are produced by plants, they do indeed retain the characteristic hydrogen isotope composition of the monsoon precipitation in their hydrogen. Similarly, we looked at, this is now work that is 10 years old, we looked at the composition of river sediments here throughout the system on the Ganges and Brahmaputra rivers, but also the mixing of the two here near the termini of these rivers. This involved filtering a lot of water because these molecules are typically quite dilute in the river load, and a lot of filtering to obtain these very large sediments that allow us to do these common specific hydrogen measurements. But the bottom line is, when you look at the environmental water composition we calculate from the hydrogen composition of these biomarkers, we end up with, here in this example, -72 per mil, we end up with compositions that are really very similar to the composition of surface waters during the monsoon. So clearly we can use these biomarkers, these vascular plant lipids and their isotope composition as a recorder of the composition of rainfall throughout the system. So before I show you that record of hydrogen isotope composition, I want to show you the record of the vegetation. And that is the record that we obtained by looking at carbon isotopes in these same molecules. So it's been well known for decades now that sometime in the Miocene C4 plants kind of took over and started to outcompete C3 vegetation in the Himalayas and many other places around the world at various points in time during the Miocene. And our record here, this is a composite record using the 3 deep sites of the carbon isotope composition of long-chain fatty acids. These molecules only produced by vascular plants. So our record really showed this very prominent positive carbon isotope excursion at around 5.6 to 5.8 million years. And this is the really well-known expansion of the C4 plants in the Himalayan foreland basin. The one point that is interesting is that our record is putting that expansion more towards 6 or even a little after 6 million years ago, while earlier work from the distal Bengal Fan was putting that more towards 7 or 7.5 million years ago. And also it shows the really abrupt nature of this change. Obviously, this is difficult to do detailed work with these Turbidite records, but we have this very abrupt transition towards C4 at that point in time here. And I'll come back to this in terms of trying to understand what has driven this C4 expansion in this system and how evolution of the monsoon has or hasn't played a role in pushing the system towards the evolution of C4 grasses. Okay, so this is the meat of the talk here with the plot of the hydrogen isotope composition of these long-chain fatty acids, so these molecules only produced by vascular plants, delivered to and preserved in these sediments at 8 degrees north in the Bengal Fan. So this is all the data that we have. We haven't done a very nice work, trying to do any sort of detail over any time period in particular, but we were instead trying to have a broad brush record throughout the last 20 million years. So to make sense out of these data, I'm going to put them in the context of what we know about the composition of these molecules in the modern river systems, as well as in record of the last 20 kiloyears that spans the last deglaciation. So this is here, this band, purple band is the composition of these fatty acids in modern Ganges-Brahmaputra rivers that we have sampled over the last 10 or 15 years, 20 years. And you can see that by and large, the vast majority of the measurements that we have from the record at 8 degrees north is in line with the composition of the modern Ganges-Brahmaputra river. So just from this basic observation, it looks like the majority of the record we have precipitation that resemble those that are characteristic of the modern system. Therefore, you can start to infer a very strong, or at least similarly strong as the modern one in terms of the monsoon intensity. We can put that also in the context, and I was saying, of a record of the last 20 kiloyears from a little bit of fan that we published a few years back. And here I'm not showing the record itself, I'm just showing the characteristic composition of the extremes of that 20 kiloyears record, which is the last glacial maximum, during which the delta D of these fatty acids is the least negative, and also the mid-Holocene, maybe around 5,000 years ago, when the delta D of those fatty acids is the most negative. So Again, almost all of the measurements that we have from 8 degrees north over the last 20 million years are contained between the variability that we see over the last 20,000 years, with really strong monsoon here in Miocene, in Holocene, excuse me, and comparatively weak to perhaps suppressed monsoon at the last glacial maximum. And I'll get back to that. Okay, so we can go one step further and try to calculate composition of environmental water using the fractionation factors that have been established for various plants, and so go from the delta D of those fatty acids to delta D of water. And when we do that, we get to this type of plot. So it looks the same, except the scale has changed. And again, I'm showing the modern rivers, the mid-Holocene and the Algae. And then once again, what you can see is that by and large, the vast majority of the compositions that we infer from those fatty acids resembles the composition in modern rivers and of the monsoon that we know of currently. However, one thing that is really interesting is that you can see in the last 2 million years, and I'm not going to go into arguing about exactly when that happens, because again, we haven't yet done a really nice detailed work looking at those transitions. But clearly, we see in the last 2 million years that there is a whole bunch of compositions that are much less depleted in deuterium. And that seems to resemble the compositions that we found typical for the last glacial maximum for the Earth fan. And so clearly in the last 2 million years, and this is here the global context with the benthic delta 18 stack, again, what happens is that for most of the record, even though there is very significant climate variability and climate cooling, which intuitively could have a very profound impact on the monsoon, it doesn't seem like the monsoon is responding, at least not rainfall as seen from its hydrogen isotope composition. However, when you start somewhere around the Pleistocene transition, when you start to have a very large glacial interglacial climate variability, climate cyclicity, then you start to see much more variability in terms of the hydrogen isotope composition of precipitation in the system, and the increase in variability is explained by the operation of these relatively undepleted compositions. So this resembles the situation of the last glacial maximum, when we think the summer monsoon had a very, very reduced intensity. Okay, so I want to go back and spend a few minutes on this question about the expansion of C4 plants. This has bugged people for a long time as to what has driven that C4 plant expansion. And one very, very popular hypothesis has been and remains that it was driven by a change in water stress, because C4 plants are much better adapted to water stress than C3 plants. And so an idea was that an increase in water stress somewhere in the Miocene, the late Miocene, might have pushed the system towards a C4 grassland outcompeting C3 forests. So here I'm showing the two records side to side, the delta C13 record of long-chain fatty acids that shows expansion of C4 plants somewhere around here. And on the left-hand side, the delta D record of the exact same long-chain fatty acids. And what you can see is that here at 5.8, 5.6, 5.8 million, when the C13 shifts, we see absolutely nothing in the delta D. So if you take this for face value, and if you look at it at this scale, which is, again, a very, very broad scale in terms of the temporal resolution of these records, it doesn't look like there is any major hydrological reorganization here in the Miocene that might explain why the ecosystems are shifting from C3 forests to C4 plants. I apologize for the really crappy looking plot here, but this is just grab this this morning from Paleo CO2 project. It's a really cool website that summarizes all of the CO2 proxies. This is just to show I'll talk about another popular hypothesis, which is that it is a drop in PCO2 that has favored C4 plants because they do have a CO2 concentration mechanism that gives them a lead in low CO2 conditions. Ironically, you can see that either the boron isotope derived or alkinone delta cytokine derived CO2 data that we have a big gap right in the interesting time period. However, what I want to say here is that very clearly in the early and middle Miocene, there is now solid evidence for low CO2 and that really predates the expansion by many million years. So I think this gets to show we have to fill in these gaps, but this gets to show that it's quite unlikely that CO2 alone would explain this C4 transition here. What we did find, though, is that right around the time of the C4 expansion, or maybe before, there is an increase in the concentrations of molecular compounds that we know are related to fire intensity. And so this is here showing the normalized abundance of these fire proxies, if you wish. And you see this increase right here that even seems to precede the trend in the precipitation here. Again, this is the same. These are the exact same samples that we've used for both measurements, so there's no question about the timing here. And this is something that has also been seen by Alison Karp and Kate Freeman in a couple of papers looking at the distal fan on the seawalls, where they see the similar increase in fire intensity throughout the recall. So it seems like there is a pretty important role of fire in terms of clearing the forest and making room for the expansion of the C4 plants. And then just for fun, I wanted to re-show this plot that Anne showed a few weeks ago when she gave her talk, whenever it was, lost track of time. So this is a record from U1448 here at the edge of the Andaman Sea. And it shows, this is the 5 million to 6.2 million time interval. And it shows several really interesting things. And first of all, there is this massive drop here in the calculated delta rate in seawater that is right around the time of the expansion. Remember, my estimate is 5.6 to 5.8, so in this time interval right here. Secondly, there is this big change in amplitude of the variation in delta rating, plantic minus benthic. And that really shows a different response to the forcing and increased seasonality. And at the same time, there is this big warming event right here. So I think that it gets to show that there is really interesting things that happen in the system. It's unclear to me what exactly, and it's unclear to me why we're not seeing it on delta D of the fatty acids. Maybe we don't have a resolution. But it is possible that these reorganizations here in the climate system might have played a role in helping in the C4 expansion. I especially like the idea that seem to be some kind of monsoon failures during these TG events. So one might imagine this might have played an important role in just pushing the system, tipping the system towards C4 plants. How am I doing on time? I think I'm pretty much up against the time limit. So I'm just going to skip this and go to the end. What we've done is we've built a record of the composition, the isotope composition of precipitation throughout the Himalayan foreland during the last 20 million years, and we found these really depleted hydrogen isotope compositions that are very characteristic of the modern monsoon precipitation. So that in and of itself suggests that the monsoon was strong and probably comparable to the monsoon we know of today throughout much of the last 20 million years. We don't have any evidence for strengthening or weakening, for that matter, in the late Miocene, and so that gets to show that wind and precipitation don't seem to tell the same story. The big ecological transition with the expansion of C4 plants in the late Miocene appears to be fairly unrelated to a large hydroclimate reorganization, but perhaps there is some role for smaller scale reorganizations that we can't see at the scale of what we record. But there is good evidence that increase in fire intensity and frequency has played an important role. But it remains to be understood why the intensity and frequency of fire has increased. And then finally, our record shows this increased monsoon variability somewhere around starting at the Paleo-Pleistocene transition. And it shows a system that becomes much more dynamic with something that resembles glacial monsoon failures that maybe happened during the ice maximum. And so with this, I just want to thank IODP, NSF for funding, all of the science party, and then all of the students and the technical staff for help. And happy to take questions.
That's fantastic. Thank you very much, Valier. If anybody has questions, please ask yourself or send by chat if you want to ask. If you want Valier to ask following the chat messages. I see there are quite a few already, but if there is anybody that wants to ask directly, please do so.
So Valier, this is Prashanta from ISER Kolkata. Can I ask my question now?
Sure, go ahead.
Yeah. So did you good talk. So did you measure the alkane fraction in the organic carbon?
Yes, we did. I didn't have time to show it today. I didn't want this to be an organic geochemistry talk because I knew a lot of people interested in the climate dynamics would be here. We did measure the alkane fraction. It shows basically the same thing. We don't nearly have as many data as we do for fatty acids. That's why I haven't focused on this, but basically it shows the same thing for both carbon isotopes and hydrogen isotopes. And the preservation is excellent, unlike the problems you can see for leg 116 in the very southern edge of the fan when there is some diagenetic issues, alterations. Here the preservation is really truly exceptional, even for functionalized lipids. All the way throughout the last 20 million years.
Okay, so what do you think? Like, can we separate the fire activity or forest fire activity from hydroclimatic condition?
Yeah, I mean, it is a bit of a chicken or egg type of problem in the end because you need to explain why the fire intensity or activity has increased, and yes, one likely hypothesis would be some drying that would have led to this increase in fire intensity. So it's not easy to understand, what is the chicken and what is the egg in this case. I think we need to do some more work, detailed work around the transition, because maybe there is some climate signal there, but that we're not seeing it at the scale we're looking at.
Okay, thank you.
Sure.
Peter?
Yeah, Valier, I guess I was interested in the fact that you're showing this big carbon isotope shift, but we don't see that in the eastern part of the Foreland Basin, do we? The Grenoble people, Natalie Vogely and friends, they were showing that there isn't a shift like that in the Brahmaputra, and I thought that a lot of the sediment and water in the Bengal Fan is coming from the Brahmaputra. So I just wondered where you think your signal is coming from. If it's not from the Brahmaputra, does that mean it has to be the Ganges?
Yeah, that's a good question. The data that we have, it is quite interesting. Maybe you can show the plot. If we look at the C13 plot, what you see is this very typical pure C3 values all the way up to the transition. And then once it shifts to something that is always mixed. So it never goes to pure C4. Pure C4 would be, for fatty acids, long-chain fatty acids, somewhere, minus 18, minus 20, minus 21 maybe. So it always goes to a mixed signal. And there is a lot of variability in there. It spans 6, 7 per minute. So depending where you look at, you take this data point or that data point, there is huge variation in how much C4 you have in the blend. So I think that really leaves room for, mixed signals from the Ganges and the Brahmaputra, where you would have, much more C3 in the Brahmaputra, more C4 in the Ganges, and variation in source could explain some of the variability here we see after the transition. That's entirely possible.
Thank you very much.
And that variability affect the delta D preferentially?
Yes, it does. It does. So for sure, some of the variability we see in delta D can relate to sourcing and or plants. That's most definitely true. But we see some, if we zoom on the last 5 million years, you see some features that resemble, this like inverted C shape that you have here in the last 4 million. That resembles some of, for instance, your record with Andonley offshore the Mahanadi. So I think there is some regional signal in there, but it's messy because of all of the complicating factors with sourcing and such.
Thank you. There are quite a few questions. So Peter asked, Ed Hathorn points us to a paper, and there is a question from YR. I don't know who he is, but you can read it if you.
Oh yeah, so the question is about the controls of the delta D in terms of the monsoon versus the dry season, and specifically, wouldn't the wet season rain not change much, but the dry season rain change instead? Yeah, that's possible. I mean, you can get to a weighted annual average composition in many different ways. But if you look at the modern system and try to understand what controls delta D in the modern system, the water budget is so dominated by the annual water budget is so dominated by the summer monsoon that it would be very hard to change the overall composition by changing the dry season compositions. There's not enough rain during that non-monsoon time period to make a difference on the annual budget.
And a question from Najender Nath, is there any control that C4 expansion has on the oceanic biogenic blooms?
I mean, it's hard to tell. I mean, there's that will have to be through nutrients, and for sure, those grassland ecosystems they do differ in their efficiency of nitrogen uptakes and or even carbon uptakes and things like that. So I suppose it's not entirely out of question that you would have a systematic change in nutrient load that is associated with the C4 expansion, but I haven't really considered that like beyond those like really basic considerations.
Yeah, at the same time, at about 5 million years, the biogenic blooms are seen in the oceans. So I was thinking any relation between the C4 expansion and the oceanic biogenic blooms. And nearly same time, you have the biogenic blooms in the Indian Ocean too.
Yeah, so I mean, then you're back to the chicken or egg problem, right? Where you could have the biogenic blooms that are slave to the larger organization of the climate system, and that also drives the C4 expansion, or you could have some feedback that is stemming from nutrient inputs. I don't know.
Thank you.
Another question from Vijayananda.
How do you manage to disentangle the isotopic composition of biomarkers from the Himalayan and the peninsular region? That's a great question. So this is something I have not shown at all. The turbidites that we looked at and that I presented data for today, we do have independent evidence that they really very dominantly derive from erosion of the Himalayas. The hemipelagic sediments, we also looked at them actually, some of them, and they have a very different composition, both in terms of mineralogy and you know, those proxies for provenance, but also in terms of the composition of the organic matter. So if you look at the terrestrial biomarkers in hemipelagic sediments, they appear to be much more looking like dry conditions, more C4s certainly after the C4 expansion. So this is a really great point. You know, we did make sure that for those turbidites we were looking at Himalayan signal. But if you don't pay attention and you start to look at things that are slightly more hemipelagic in nature, and at the top of the Buma sequence, it can be difficult to, disentangle the two. Then you can have some sourcing effects, and most likely, yes, there is some signal from peninsular India where it's over drier.
Thank you, Valier. I think you've gone through most of the questions. I think Vijay asked a clarification.
Any effect of thermal alteration? Not at those sites. I mean, again, as I was telling Prasanthya, the thermal maturity at those sites is remarkably low, and this is quite different from either the Seawollic records or the distal Lake 116 records in that regard. So I mean, it's quite remarkable. You look at those lovely sediments from the Miocene at about a kilometer depth below the surface, the water sediment interface, and they are barely consolidated. It's pretty crazy. So temperatures are low, compaction is really minimal. It's really the best case scenario in terms of having preservation of the organic signatures in these sediments.
So this is to mention for people who didn't read the question. It's about the thermal alteration of plant biomass in the sediments. So they are pretty fresh.
Yeah.
Any other questions?
So Valier, do you think if you have forest fire and that will not alter the isotopic composition of the biomolecule?
So Kate Freeman and her group, they looked into this by doing a little bit of carbon isotope work on those fire proxies, on those pHs, and it shows that you really drift toward more and more of a C4 source in terms of the fires, like very early on. In terms of the budgets, I really don't think that I mean, those pHs that derive from fire, they are very minimal in concentration. So we're not looking at, I don't think the bulk of the organic matter is impacted by the burning, if you wish.
Okay.
Otherwise it could, but it's not that big. I mean, people that have looked at that have burned vegetation and looked at carbon isotopes, they didn't, there's like a few per meter, but it's not that huge actually.
Okay. Thank you.
Sure.
Well, thank you again, Valier, for a fantastic talk.
My pleasure. Thanks for the opportunity to give this talk.
We will return next week on Schedule B, and it's going to be Eocene soon with talk about Lus and monsoon in Lus. Please thank Valier for his excellent presentation, and see you next week.